This is Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on deriving the kinematic equations. Alright, so we've collected data, position time graph. We created a position time graph. We found our mathematical model for the position time. And we found that the data that I used, which is different from the video, gave us an equation of x is equal to 0.35 meters per second squared times t squared. And from this graph and data, we collected velocity data by finding the slopes of all these individual tangent lines along the individual times that we had for each position. So we had a data table of time in seconds, position in meters, and velocity in meters per second. From this, we created a velocity time graph, and we also created a velocity position graph. Once we plotted our data, we found that velocity time was a direct relationship. So as a velocity is directly proportional to time, which means we start with y equals mx plus b. Substituting in, we replace y with velocity. The slope, we figure out the units on the slope, meters per second, so we flip and multiply, we get meters per second squared. It happens to be your same units as we had in the position time squared graph. So we're going to again use a slope so that our values work out as 0.7 meters per second squared. Takes care of the slope. We replace x with t. And our vertical intercept we can see here is 0, so we don't need to write it. Now our velocity position graph, we have a shape that looks like a side opening parabola. So we go to our graphical method summary sheet and we can see that velocity squared is proportional to x. So we start with our mathematical model. And now we're going to look at the units. So we look at the linear version of the graph, which is going to be v squared versus x. The units are going to be meters squared over second squared when we square the velocity divided by meters. When we flip and multiply, we can see that simplifies to meters per second squared. The same unit we had on both of the slopes on velocity time and position time squared. Now the unit or the number we're going to use is 1.4 meters per second squared, and that writing our equation out so that we don't forget, y squared equals mx plus b. We used v squared in place of y squared, 1.4 meters per second squared in place of m, and x stays x. Now the vertical intercept is 0, so we don't have to worry about writing plus 0. So these are the specific equations. So the slope of the velocity time graph is the value called the acceleration. So we're going to write this equation first, as it is listed first on most formula sheets that you would have for the kinematic equations. So most formula sheets have the symbol of Vx. Now, if we did not have an initial velocity of 0, our car didn't start from rest, we'd have Vx naught. That just represents the horizontal velocity at time 0, so the initial velocity. Then we can know that the slope represents the acceleration. So we're going to add the acceleration in the x direction, the subscript of x times t, and this is our first kinematic equation. So we're going to go to our position times squared graph and look at this slope and compare it to the value of the acceleration. And I can see that the value 0.35 is about half of the acceleration which we defined as the slope of the velocity time graph. So we're going to go ahead and write x is equal to our vertical intercept, which is the initial position, x naught. Now, to find the rest of the equation, we're going to use the velocity time graph. And we know that on a velocity time graph, the area underneath the velocity time graph is the displacement or the change in position. So I'm going to look at this area here, and I'll break it down into a rectangle and a triangle. And I'm going to add these two values to the initial position. So I can see that the area of the rectangle is just the initial velocity times the time. That's the area of the rectangle. So that's the first part I'm going to add, is initial velocity times time. Plus, I can find the area of the triangle, which is delta v and delta t. So 1/2 the height times the base is going to give me 1/2 delta v times delta t. but we've got this 1/2 a and t squared. So where does that come from our previous equation? Well, let's look at our equation for the first kinematic equation. If we rearrange this, we can see that the acceleration is equal to change in velocity divided by change in time. And if we multiply by both sides by time, we end up with the delta v, or the change in velocity, is equal to the acceleration times the time. So I can substitute that in here. So I substituted a in a times t for delta v. So now when I simplify that, I end up with my second kinematic equation, which is found usually second on formula sheets, which is why we're deriving them in this specific order. So now let's go ahead and look at the velocity position graph. Let's compare this slope to the acceleration. So I can see 1.4, that's double 0.7. So that means my slope over here is twice the value of the acceleration. Writing the general equation, vx squared is equal to a vertical intercept, which is going to be the velocity squared, the initial velocity squared. So we'll write that as vx naught squared. And our slope, we represented that 2 times the acceleration times the displacement times x. And normally you're going to see this written as the final position minus the initial position. And this gives you your third and final kinematic equation. And all of this is derived simply by rolling a car down a ramp and collecting simple position and time data, finding slopes of tangent lines, and creating some graphs. So these are your kinematic equations and how they're derived. Have a great day and an even better tomorrow.
If you found this video helpful, don't forget to subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.